Hi everyone, I'm Jay Fu, and the paper I'd like to introduce today is Perceiver IO, which is a general architecture for a structured input and output summary. So before we really started, can you recall the architecture of transformers, like some of the components? Yeah, so we have feed-forward and attentions mechanism, and also linear layer and softmax and things like that. Basically, just encoding and decoding parts. And as the current architecture cannot apply beyond a small set of stereotype settings, and our baked-in domain and task assumptions were scaled poorly to large inputs and outputs. So the researchers would like to propose a more general purpose architecture that handle the data from arbitrary setting while scaling linearly with the size of inputs and outputs in this paper. So it's actually doing the fully attention read, process, write architecture, and they propose that the actual architecture can be applied with unprecedented level of generality. So do you have any idea probably when is the earliest trial to realize this kind of high dimensional inputs take place? Yeah, so it's actually from last century, 1994. Some researchers proposed autoencoding, and for the following years, researchers have always been working on this, especially after the invention of neural network. And several groups have proposed to use attention to manipulate the size of an array to introduce bottlenecks in processing. And since 2017, there are researchers and other groups proposed some solutions to solve tasks in multiple domains, which is kind of similar to this one. So for the perceiver IO architecture, we can see it has an input array, a latent array, and those two were put together to the encode chunk. And after the perceiver IO, it can be processed here in the purple chunk for several times, like L times. And then they were passed to the decode part together with the output query array. And for all those part, we have global query key value attention operations for this. And it's the calculation inside is a little bit complex, but yeah, it's then followed by a multi-layer perception, which can be regarded as a fully connected CNN. So for discussion here, with transformer, why we have limited text size, or why transformer isn't all we need. It is because the self-attention mechanism, it scales very poorly in both compute and memory. So in every layer, all inputs are used to produce query and keys for which a pairwise dot is computed. Hence, it is not possible to apply self-attention on high-dimensional data without some form of pre-processing. And this kind of dot production is actually take place here. And then it was used to calculate the attention scores. So the perceiver IO uses attention non-homogeneously by mapping inputs to a latent space, processing in the latent space and decoding to an output space. So it has no quadratic dependence on the input or output size, while the latent attention is independent of both input and output size. As a corresponding reduction in compute and memory requirements, it can scale to much larger inputs and outputs. And then basically for these two parts is still describing the structure, architecture of the perceiver I/O. And after all this, the researchers made several experiments for language, optical flow, multimodal, autoencoding, and things like that. And if you're interested, you can go search the paper and try this out. So in conclusion, in this work, the researchers introduced perceiver I/O, which is an architecture capable of handling general purpose inputs then output while scaling linearly in both input and output sides. This architecture achieves good results in wide range of settings and making it promising candidates for general purpose neural network architecture. So perceiver I/O leverages the express power of latent attention and use learned queries to expose a sample and unified interface that can handle multimodal and multitask settings. So overall, the perceiver I/O offers a promising way to simplify the construction of sophisticated neural pipelines and facilitate progress and multimodal and multitask problems. So a little bit critical analysis here. I think the good side of the paper is it is novel and solid, and also it is tested on massive experiments, including language understanding tests and all of those. So, however, I do think there might be some weakness of the paper, like although it removes the task-specific pre-processing, it actually still requires huge engineering efforts to adapt model for different tasks. And it actually didn't discuss for tasks that require more information on prior decoding context, whether the proposed model can still perform well on those tasks. And so I attached a link here, and if you're interested in, you can definitely try this out and read the whole paper. And thank you for listening.